Light. It bathes our world in warmth and illuminates our lives, casting a golden glow that transforms the ordinary into the extraordinary. But have you ever stopped to consider the magic it holds? The way it can change our perception, our mood, and even our understanding of the universe? A simple beam of white light, seemingly pure and uncomplicated, possesses a hidden wonder, the potential to transform into a dazzling array of colors. This transformation is not just a visual delight, but a gateway to understanding the very fabric of our reality. This transformation, this splitting of white light into its colorful components, reveals the captivating beauty of a fundamental scientific principle. It's a phenomenon that has fascinated scientists and artists alike for centuries. We've all witnessed this phenomenon, whether catching a glimpse of a rainbow after a summer storm, a fleeting moment of nature's artistry that leaves us in awe, or marveling at the way sunlight dances through a crystal, scattering light into a myriad of colors that playfully decorate our surroundings. But how exactly does this magical transformation occur? What is the science behind this enchanting display? What causes white light to unveil its hidden spectrum, painting the world with vibrant hues? The answer lies in the interaction between light and matter, a dance of photons and particles that reveals the hidden beauty within. Join us as we delve into the fascinating world of light and color, exploring the scientific principles that govern this captivating phenomenon. We will journey through the history of light study, from the early experiments of Isaac Newton to the modern-day applications in technology and art. We'll unravel the mysteries of white light, understanding how it can be both a single entity and a spectrum of colors. Unlock the secrets of prisms, those simple yet powerful tools that reveal the hidden spectrum within. And discover how nature orchestrates its awe-inspiring light shows, from the rainbows that grace our skies to the subtle play of light in the dewdrop. Let's embark on a journey of scientific discovery, where the beauty of the natural world intertwines with the elegance of scientific principles. We will explore how light influences everything, from the growth of plants to the way we perceive art and architecture. Let's explore the magic of light, a force that shapes our world in ways both seen and unseen, a source of endless wonder and inspiration.
We perceive white light as pure and singular, but it holds a secret. It's a blend of all the colors we see in a rainbow. This seemingly simple light is actually a complex combination of various wavelengths, each corresponding to a different color. Imagine a painter's palette, swirling with vibrant hues, all combining to create a seemingly pure white. That's white light. Just as an artist mixes different colors to achieve the perfect shade, nature combines different wavelengths to produce white light. Each color in the spectrum, from red to violet, has a different wavelength. These wavelengths are part of the electromagnetic spectrum, which includes not just visible light, but also other types of waves like radio waves and X-rays. Wavelength is the distance between two peaks of a wave, and it determines the color we perceive. The longer the wavelength, the redder the light. The shorter the wavelength, the bluer or more violet the light appears. Red light has the longest wavelength, while violet has the shortest. This range of wavelengths is what makes up the visible spectrum, the part of the electromagnetic spectrum that our eyes can detect. When all these colors of light, each with its unique wavelength, travel together, they blend seamlessly, creating the white light we see. This blending is so perfect that we often don't realize the complexity hidden within what seems to be a simple beam of light. But this hidden rainbow within white light can be revealed under the right conditions, like when it encounters a prism. The prism bends the light, separating it into its component colors, allowing us to see the individual wavelengths. So white light isn't as simple as it seems. It's a complex and beautiful phenomenon, a testament to the intricate workings of nature. It's a harmonious blend of colors, each contributing to its pristine appearance. Each color plays a crucial role, and without any one of them, the white light would not be the same. The secret lies in separating these colors, allowing us to witness the full spectrum hidden within. By understanding this, we gain a deeper appreciation for the complexity and beauty of the light that illuminates our world.
A prism, often made of glass, is a simple yet powerful tool that unlocks the secrets of white light. Its triangular shape, with two angled surfaces, holds the key to revealing the hidden spectrum. When white light enters a prism, something remarkable happens. Instead of passing straight through, the light bends or refracts. But the key to the color separation lies in the fact that different wavelengths of light bend at slightly different angles. This difference in bending, called dispersion, is what causes the white light to fan out into its component colors. Red light, with its longer wavelength, bends the least, while violet light, with its shorter wavelength, bends the most. The result is a breathtaking spectacle. A continuous spectrum of colors from red to orange, yellow, green, blue, indigo, and violet emerges from the prism. The once hidden rainbow within white light is now revealed, painted across a surface for all to see.
Section 4. Bending light, refraction and Snell's law. Refraction, the bending of light as it passes from one medium to another, is the central phenomenon behind the prism's magic. This bending occurs because light changes speed when it moves from one medium to another, such as from air into glass or water. The change in speed causes the light to change direction, creating the beautiful effects we see with prisms and lenses. When light travels from air into a denser medium like glass, it slows down. This slowing down is due to the optical density of the medium, which is a measure of how much the medium can bend light. The denser the medium, the slower the light travels through it. This change in speed causes the light to bend. The amount of bending depends on the angle at which the light enters the new medium and the difference in optical density between the two media. This is why light bends more when it enters a medium at a steeper angle. The angle at which light bends depends on both the angle at which it enters the new medium and the difference in density between the two media. This relationship is crucial for understanding how lenses and other optical devices work. This relationship is described precisely by Snell's law, a fundamental principle in optics. Snell's law provides a mathematical formula that relates the angles of incidence and refraction to the refractive indices of the two media. Snell's law provides the mathematical framework for understanding how light bends at an interface. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant and is equal to the ratio of the refractive indices of the two media. It allows us to calculate the angle of refraction based on the angle of incidence and the refractive indices of the two media, which represent their ability to bend light. This calculation is essential for designing lenses and other optical devices that rely on precise control of light paths. In the context of a prism, Snell's law explains why different colors of light bend at slightly different angles. This phenomenon is known as dispersion, and it occurs because different colors of light have different wavelengths. Each color has a slightly different wavelength, and this subtle difference leads to different degrees of bending. For example, blue light, which has a shorter wavelength, bends more than red light, which has a longer wavelength. This difference in bending, or dispersion, is what allows the prism to separate white light into its component colors. By understanding and applying Snell's law, we can predict and manipulate how light will behave in various optical systems, leading to advancements in everything from eyeglasses to advanced scientific instruments.
Section 5. Rainbows, Nature's spectacular light shows. Rainbows, nature's own breathtaking light shows, are spectacular examples of light dispersion in action. These colorful arcs, appearing in the sky after a rain shower, demonstrate the principles of refraction and reflection on a grand scale. When sunlight enters a raindrop, it encounters a change in medium, similar to what happens in a prism. The light slows down and bends as it enters the denser water droplet. Inside the raindrop, the light reflects off the back surface of the droplet and travels back towards the edge. As it exits the raindrop, it undergoes another round of refraction, bending once more as it enters the air. This twofold refraction, combined with internal reflection, disperses the sunlight into its different colors, creating the rainbow. Each raindrop acts like a tiny prism, refracting and reflecting light to produce the colorful arc we observe in the sky. Have you ever noticed a natural prism in your everyday life, like a rainbow or light through glass? Share your experience in the comments below.